Bienvenido a un nuevo contenido de Uninorteco. No olvides suscribirte a nuestro canal.
Welcome. Thank you for attending a new session of PiA webinar series. Before introduce our speaker, I want to remind you that Partículas in the Americas is an academic joint initiative supported by Asociación Argentina de Sedimentólogos, SINESTAD from Mexico, Escuela Politécnica Nacional from Ecuador, Instituto Argentino de Oceanografía, Instituto Geofísico del Perú, Mississippi State University from United States, Universidad de la República from Uruguay, Universidad Federal do Espírito Santo from Brazil, Universidad del Norte from Colombia, and Sequoia Scientific Inc. We want also invite you to visit our new webpage. In blue, you can see the link. In this webpage, you can find information about our goals, about our activities, and periodically you can find information about the scholarship, position information, and recent publication of sediment dynamics along the American continent. For example, you can see the information related to the PiA webinar series. You can find past webinar and upcoming webinar. You can also revisit the broadcastings. You can click on the title and on the YouTube icon if you can watch again this presentation. We want also invite you to join us in social network, which is also new. You can visit us on Facebook, Twitter, on LinkedIn, because one of our goals is to create a community to interchange information about sediment dynamics in America. Well, today we are glad to present you the Professor Ashish Mehta, which is going to present some observation on the effect of water temperature on the movement of fine sediment particles. Professor Ashish Mehta is an emeritus professor at the Civil Environmental Engineering Department from the University of Florida. He holds a bachelor's and a master in chemical engineering and a doctoral degree in civil engineering. As a coastal and oceanic engineer, his research was mostly focused on coastal cohesive sediment transport, coastal processes, and port and harbor engineering. Among the important achievements he awarded, he was honored with the Hans Albert Einstein Award in Hydraulics and Sediment Transport in 2000. Dr. Mehta has been recognized to offer an important box to the complex research areas he has been immersed to make the science mature and independent. So, Professor Ashish Mehta, thank you very much for attending our invitation. It's a great pleasure to having you here. And please, let's talk to sediments.
All right, thanks a lot, Juan, and also Yogi for inviting me. When I was asked to give a talk, I decided to speak on the effect of temperature because it's obvious that there is a lot of interest in the topic for a variety of reasons. And so let's start with some general observations, and then we'll go into some issues that need to be dealt with because this is a fairly new field in a sense. In a sense it's not, but in a sense it is for fine sediments. And not a whole lot of information of the kind needed for comprehensive evaluation is available. So let's start with the temperature rise. This particular plot that you see is shows two sets of curves, the red one and the blue one.
Professor Mehta, excuse me. You have
Yes.
to share your screen. We
Say
are
that
not.
again?
Yeah. You have to share your screen.
Okay. So where is the sharing? Okay.
Yeah. In the bottom panel, you can see the option to share the screen.
Yeah. Yeah. Okay. Okay.
Yeah.
But
Now we can see. Yeah. You can project the slides.
now I can go back to my slides,
Yeah.
because when I see my slides, I cannot see you. That's okay, right? So.
Yeah. Yeah. It's okay. Don't worry.
So can you see the chart now? The slide? No.
Yeah. We can see.
You can see now. So
Yeah.
you can see that there are two. Hello. All set?
Yeah. We can see. You can
Hello.
go on.
Okay. All right. So you can see that there are two sets of curves, the red one, the red lines and the blue lines. These are actually, obviously, they are projections based on uh, data from 1970 greenhouse gas emissions. And so these are global climatological models. And there are two sets. One is the CMIPS, which is a group of 26 models, and the other one, CESM lens, is a single model. But what they did was to make 30 different runs. So in one case, in the case of the blue lines, it's a single model with different scenarios run. And the red lines, they are actually different models. So the difference in the output is due to the fact that the 26 models have different physics in them. So the spread of the upper and lower bounds of the predicted temperature range is much more erratic and wider in the case of the 26 models, because they have different physics. In any case, the point I'd like to make is that whether you look at the blue bounds, the upper bound and the lower bound, or you look at the red bounds, upper and lower, the difference in the temperature, the range of temperature between the upper and the lower is between 2 degrees and 3-4 degrees or something like that, 4-5 degrees. Now this is actually quite substantial, but what we need to look at is that this range of values is well within the range of values that we experience here on the planet. So here you look at some data from Hudson Bay, and some data were taken in November, December, and some in August. And you can see an 18-degree drop in temperature between the two seasons, and which is much wider than the 4 to 5 degrees Celsius that we looked at in the previous diagram. So what it tells you is that you can actually, nature provides us with a laboratory where we can look at the effect of temperature on any processes, including sediment transport. And so some of them have to be done in the lab, but we should not forget the fact that nature provides us with a laboratory where we can study a wide range of phenomena as far as sediment transport is concerned. So here but there are some glitches. For example, if you look at this particular piece of work, what they found was, what they were looking for was a sand transport along this beach in Hudson Bay. And they found that the sand drift was much less in December than in August. And what they concluded from the observations was that it had to do with this huge range of temperature difference between the two seasons. But in my personal opinion, I don't think that this necessarily is the only reason why you would get such a big difference in sand transport rates. What I did was let's calculate the Reynolds numbers. So here we have a Reynolds number which is about 5.5 times 10 to the power 5. And in summertime, it's 9.1 times 10 to the power 5. So in both cases, the Reynolds number are quite high. So it's not like we are shifting from intermediate range to fully turbulent range or something like that. So it can't be that this viscosity difference, which we are looking at here, is the only reason for the possible effect of phenomena on the transport rate. But the point is that on the one hand, nature does offer us the opportunity to look at wide range of temperature conditions, but at the same time, interpretation has to be really careful. And in something like this, I would think that we would have to take a lot more data on waves and currents and so on and so forth before we can actually conclude what are the reasons why the sand drift rate was much lower in winter than in summer. So now with that brief introduction, well, let's look at the type of sediments that we are talking about. Here we have diameter in microns on the left-hand side. And this particular classification first starts with the classical soil mechanical categorization, that is, soil is sand, silt, and clay, and so on. But in fact, what you look at when you look at the right-hand side here, the cohesion part of it, these sediments up to about 62.5 microns, which is more than silt, they are cohesionless, and then below that you start getting some cohesion, and then these are cohesive sediments. And then when you go below about 0.1, then you don't have a sediment. It's because particles less than 0.1 are colloidal and they simply don't settle. So we don't even talk about sediment. So we are interested in this particular range. And as you know, this range is where electrochemical forces are important, but also adhesive forces due to biota, and we'll be talking about that. But so adhesion and cohesion and adhesion both are important in this. And so when these forces become important, you have to think about the effect of temperature on those forces, which is what one needs to look at to actually ultimately predict transport rates for cohesive sediments under different temperature conditions. So let's look at the next slide. So here, let's talk about some simple issues. Talk about erosion. Before we do that, the question is how does temperature enter into the equations? Well, it's quite well known. The kinetic energy per molecule of mass m and vector velocity u is 1/2 times m times u squared. So, and we also know that the distribution of the molecular energy, whether it's in gas, in liquid, or in solid, is Boltzmann distributed. And for that case, you can show that this kinetic energy equation here, from that we can derive the mean kinetic energy, which is 3/2 kappa times the absolute temperature, where kappa is a Boltzmann constant, which is the gas constant divided by Avogadro number. Anyway, to make a long story short, all of this leads to what is called Arrhenius equation, and this was figured out by Eyring and his co-workers in chemistry in Europe in 1930s. But the Arrhenius equation basically says that the rate of chemical reaction increases with temperature, which is of course known, but what they did was to find an analytic expression for the rate of chemical reaction as a function of absolute temperature. Now then, back in Berkeley, back in the 1960s, Professor Mitchell decided that we could as well apply it to cohesive sediments rather in general, or cohesive sediments in particular, because we are talking about chemical forces again, and so we have a fluid stress which tries to break up the bonds, and then we have these short range forces which try to bring them together, like the van der Waals forces. So he applied that, and it turns out that actually you can express the erosion rate as a function of absolute temperature, just like the reaction rate of chemicals with the absolute temperature. So here is a set of experiments where they took a circular tube and with temperature control, and they eroded the sediment, fine sediment. It's called grundite. It's a clayey sediment, by keeping the current velocity constant and increasing the temperature. And you can see that this thing goes up and up and up. And if you take these data and plot them like this, where this is the erosion rate divided by the absolute temperature, and here is the absolute temperature, then you get inverse of absolute temperature. So you get this function. Now, because it's the inverse, actually this is plotted in the classical Arrhenius form, which is this here. So it goes down, but in fact what it tells you is that the temperature, the erosion rate goes up with the temperature. So this is just to point out how temperature enters into the transport equations, in this case erosion, but it of course the temperature changes all matter, so it enters in all the processes dealing with sediment transport, and that is the reason why it's so difficult, because there are so many processes involved that if you just study one or two without looking at the feedbacks, then you found something, but then you may not be able to use it for simulating anything, and we'll talk about that in a minute. So cohesive sediments, when the temperature goes down, everything becomes less active, and when the temperature goes up, everything becomes more active. And so the higher the temperature, the more the collisions and more the formation and breakup of flocks, the flocks being the conglomerates of many particles put together. So if you do a simple experiment, here you drop this, take this tube and you drop this sediment here. If flow goes down, and you have a detector and you have a light source. And what this will do is that if the light source has constant intensity, on the other side you'll get a record, which is the light intensity as a function of time, but there is a DC component and there is an AC component. And if you had a truly uniform fall of particles, there would be no DC components. All the particles would be uniform and everything would be a DC component, no AC component. So if you increase the temperature, the AC component goes up because the flocks become more non-uniform, and some are larger and some are smaller, and so on and so forth. So what you do is you define what is called a flocculation index, which is the ratio of AC to DC, and then what you do is you put this in a temperature bath, constant temperature bath, and you see how this flocculation index changes. And so here what was done is that what they did was they took kaolinite and added alum, which is aluminum sulfate, and they put it in this little jar and have a stirrer. In the stirrer, the energy spent by the stirrer can be used to calculate the shear rate that is imparted to this jar. And so then what they did was they changed the shear rate and temperature. Well, the shear rate was not changed. Actually, what they did was they held the shear rate constant, and so then the first there was just kaolinite. Then they added alum. They added alum about here, and then you can see that aggregation, that is flocculation, takes place and goes up to this point. Now, if you have lower temperature, the flocculation index drops. So that means that the AC component is decreasing, because the decreasing temperature means that everything becomes more and more quiet. So which is what we are really interested in, because when you have summertime, everything is more agitated, and wintertime it's less. Now here what they did was they really jacked up this shear rate. So everything broke down. So all the flocks broke down, and then they started the process again. And we won't be discussing all of this, but what I want you to know is that the effect of temperature on the flocks was that the lower the temperature, the less they were likely to break up and grow, and so on and so forth. So that obviously is the reason why erosion rate changes, and that is also the reason why the settling velocities change in the environment. So you have settling velocities in winter time in an estuary versus summertime. If the difference is like 18 degrees that we noted earlier, there'll be a huge difference in the settling rates. So obviously we started out by talking about global sea level temperature rise and so on, but in fact, because the ranges are much wider already, there is already an interest in looking at the effect of temperature on transport without having to worry about the issues with climate change and so on and so forth. Although if you have more information on the effect of temperature on sediment transport, then we could do better modeling, which is where the real problem is, because we don't have that kind of information. So we can do some modeling, and I'll try to explain. This is kind of a busy slide, but it is a flocculation model. What it does is that under collisions between particles, flocks can grow or they can break up depending on what the shear rate is. So there are three mechanisms: flow shear, what is called differential settling, which means particles falling at different rates, and Brownian motion, which you are familiar with. Brownian motion is due to heat in water. Even if there is no motion of water, the molecules are going back and forth because of the internal energy, which starts at 0 degrees Kelvin and goes up. So but the point is that all these mechanisms which determine what the size and the settling velocity and all that of flocks is going to be, they're all dependent on the absolute temperature. So when you do this kind of modeling, and here is how the modeling, I'll just give you what the modeling actually shows. Here, what we are trying to do is to find this size distribution of particles. So this is the output. This is the fraction of mass, and this is the size distribution. These are all macro flocks, and then these are micro flocks, and about 100 microns. Some people use different threshold, but that's a threshold. So smaller than 100 microns is micro flocks, and larger than 100 microns is macro flocks. Now, what's going on here is that what you do in the modeling, you start with all micro flocks, and they're all bunched up here. But then you apply this flow, tidal flow, or waves, or whatever you want to, and the shear actually causes these to start flocculating, and from this, it starts moving in this direction. and then it becomes larger and larger because collisions are increasing, and then it reaches some kind of a maximum value beyond which the stress is the stress is too high for the flocks, and they start breaking down. So they go down here, and so what that means is that all you had was everything was here, and now it developed into something like a full-fledged wide distribution. So that is what is aggregation is what it's all about. And so it follows, they kind of jump, flocks form, and they bigger and bigger and bigger and bigger, and then when they become quite big, they start breaking back again. So that process, if you model that process, that is flocculation modeling, and then it develops into this distribution. So let's look at one experiment where they started out with this, all the particles were in this range, and then it developed into a mixture of microflocks and macroflocks. And this is the experiment by Toorman and his students. The same thing, you put that sediment in a jar. This jar was 10 meters in height. Okay, so it wasn't a small jar, it was huge, and many stirrers. You start out with a unimodal distribution, and everything is here. These are all small microflocks. And then you see that after about 180 seconds, you get this starts developing. So this is decreasing, and it's moving here. And then in about 1280 seconds, these macroflocks have developed. So this is what aggregation is all about. You start out with simple particles, but they will eventually develop into a distribution. And obviously, the properties of this distribution is what we want to know, because in a given environment, if the temperature is high or temperature is low, this distribution will be different. So that's what we'll come back to that in a minute. But to see that in a real situation, what was done was that Andrew Manning, his doctoral thesis, he collected samples here in the calstock, Tamar estuary calstock, and he used a device which was put in water, and this is underwater, where the flow is going like this, and there is a flap here, and there is a flap here. So with a single command, both the flaps open. So as a rule, the water is going freely, but then all of a sudden you shut the flaps, and this water gets collected here. Then you open this slide here. So as soon as you do that, the flocks start falling down, and then you have a video camera, so you can measure the flocks in the diameter and the settling velocities, and you do that in situ. So you all of this is underwater, and so when you get all the data right there and then. And he was able to collect a lot of data, not just in this estuary, but several others in Europe. And it's just let's just briefly go through what the data generally look like. If you plot the settling velocities against the shear rate, the shear rate is from tide. So as the tide increases, the shear rate goes up. As it water current slows down, the shear rate decreases. So we start with here at low water slack, and then as the current picks up, the shear rate goes up, and the flocks start building up. But they come up to this point, they are building, but now you can see that they are going down again, and that is because the breakup function is becoming stronger. The high shear rate is breaking up, so it starts dominating. So these settling velocities go down. Now you reach the maximum current. Okay, so this is where the current is maximum, and then it starts decreasing. If it starts decreasing, it does not encounter any problem from growing, because as a shear rate goes down, the flock size increases and increases and increases until it reaches slack water at high tide, and then water current stops and everything drops back here, and then it starts again. So this is a process that takes place every half a tidal cycle. So the question is, what is all this? I mean, if this was ideal, you should get all the flock should be on this line. There should be only 2 lines and so on. But it's all bunched up, and there's a whole bunch of stuff here. So the question is, what is this data spread due to? Well, obviously, the data spread, there are a number of reasons, but one reason is temperature, because they took this data over several between summer and winter, and the temperature varied between 7 degrees Celsius and 18 degrees Celsius. So what was done was, what we did was to run the model for 18 degrees and for 7 degrees. That is, the model actually simulates this thing here. It starts here, goes up and goes down. And so you can see that the curve for 18 degrees is different from the curve at 7 degrees. So, and so if you superimpose the two, you can see that the part of the spread of the data is probably due to the fact that the temperature is varying. So in winter time, you have lower settling velocities because the collision frequency is low. In summertime, you have a higher higher velocities, because there's a greater chance of interparticle collisions. So that seems like if that is the case, then we have solved a big problem. But the question is, have we solved that problem? So let's talk about, in a general sense, what are we interested in? So we are interested in knowing what will happen at the mouth of a river, let's say, when the global climate goes up, temperature goes up or whatever. But here we take this Southwest Pass. All of you are familiar with this. This is the Mississippi River. The problem with this is that this is one of the largest basins, as you know, in the world. And it's practically impossible to really study all of these things and all the phenomena and all the feedbacks to model what's going on here. So that leads us to the whole question of strategies for modeling. How do we model small systems, and how do we model large systems, and so on. And so when you study a small system and you look at simple things in laboratory and so on and so forth, it may be good for small scale problems, but it may not be good for large scale problems. But in any case, the thing to note is that temperature changes affect all matter, and number of parameters increase with system dimensions. And smaller systems are a lot easier to model. That doesn't mean they are easy. It's simply that they are easier. And but that being the case, let me just, a couple of points I'd like to make now is that we say that it's easier, but it's not really that easy, because we have this thing with Biota, so which we didn't talk about really. We talked about it a little bit in the beginning, but not later. So here is this data from tidal river in Korea, and they took the data on the flock diameter and algal count between April and December. So what you see is that the diameter in summertime, the diameter actually went up, and but the algal count also went up. So here it turns out that you see a tremendous correlation between see, the algal count is a proxy for chlorophyll. So in summertime there is, as we know, there is more chlorophyll, and so there is a lot more organic matter in suspension, and also the flocks are more organic. So So it's you might think that, oh well, the temperature is going up, so if it's purely mineral, maybe the flocks will break up or something. And but no, they actually are growing. And then again, if you look at what this is the algal growth rate here, and this is again the inverse of the absolute temperature. And again, you see that there is a big, this is logarithmic. You see, again, there is a lot of effect of temperature, obviously, on algal growth. And so, quite often these days you see in journal articles, people take a cylinder or something and they put some clay in it, this or that clay, and they measure the settling velocity and write a paper about it. And frankly, that paper has no real value, because you can't really just deal with abiotic systems in nature and expect to produce something that is meaningful in terms of actual sediment transport. So the point is that to study the effect of temperature on sediments is a big deal. It's not just electrochemical, but also you have to look at polymeric substances and so on, so the binding and adhesion and so on and so forth, to come up with something realistic in terms of transport modeling. So maybe we can do something at small deltas. And I put this one because this is very close to Yogi Agarwal, where he lives. So, but you've probably never seen it. But I'm just kidding. But this is a straight. This is on the other side of, well, it's west of Seattle, and it's a small channel, and so it's somewhat protected from wave action. And this Elva River, you see, it's very small. This is only 0.3 kilometers. So something like this, maybe we can start looking at, modeling. I think this also has a lot of mineral sediment. So that's and not everything is organic. We can do something like that with smaller systems. And what I try to do is, if you do some simple calculations of this plume that is coming out, under given assumptions, you can say, oh, well, you see, the temperature is 20 degrees Celsius, the plume length will be 6,800 meters. And if it drops to 10 degrees, then settling will be, it'll fall out faster. And so it's 10 degrees. It's much shorter, 4,000 meters. So simple systems with simple geometries and not too many parameters could be a good starting point for studying systems which in reality are much more complex. So I think that's what I had to say, but I don't know if anybody heard me or not. So we'll keep my. Is anybody there?
Yeah, of course, we are here.
Okay. I'm glad I didn't hear you for 10 seconds, and I thought maybe I'll have to do it all over again. So.
Thank you very much. It was very impressive. Thank you very much for your talk. And now we are open to questions from the public. Please remember that you can write your question using the chat, and we are going to tell the question to Professor Mehta. Okay. So Professor, in the meantime, I have one question. You made a survey on the state of the art of the sediment cohesive respect to temperature, right? And is now when you see modelers approaching to morphodynamics, evolution of river mouths and fluvial system, some of them avoid to incorporate cohesive sediment in such modelations. So
Right.
do you think we need to do to improve the model of morphodynamic evolution in river mouths, in fluvial system, in order to incorporate cohesive approximation, taking into consideration the complexity of the problem? Because you mentioned just one of the points, temperature, but there are many, as you say, organic matter content and other things. So how we can improve such obstacle?
Well, I think a lot of some of your audience, they have been attending uh, the interco meetings and other meetings like PEX and others, where there is a lot of work that is going on in many areas that includes the mineral sediments and biotic sediments and so on. But so it's not like it's not possible to do any modeling, but so a fair bit of research is going on, but much less research has taken place in the matter of temperature. And the reason obviously is that, well, first of all, you have to deal with all these other things like clay, minerals, and biota and all that, how they affect before you add on other problems like temperature. Uh, but that's the reason, and also it's more expensive to study, at least in the lab, temperature effects. But nowadays, with the kind of equipment we have in the field, what I'm trying to say is that it's possible to study many of these effects of temperature directly in the field. My guess is that it's going to take place in the near future, but so far it's been meager, less than adequate.
Okay, thank you, Professor. We have a couple of questions. One from Susana Binson. Uh, could you tell us something more about your flocculation model?
Yes, it actually is the model that Bill McAnally developed, and we recently applied that. And as I mentioned here, that we expect that article will be published, although it does not include any effect on temperature. It includes the effect of physical factors other than temperature on the settling velocities in this Tamar estuary. So but this paper gives you the diagram I showed is going to be in this new article, but the basis of that flocculation modeling is the paper from the year 2000 in ASCE. I can send it to Susanna.
Thank you, Professor. This one is from Gerardo Perillo. The actual size of the particles, how they actually affect the results of the model. For example, larger, still cohesive particles will be less prone to be affected by the temperature.
Well, I'm not sure. The particles are all porous matrices. They are. I guess I didn't quite follow the question, but the particles are all the larger particles are. The larger the particles, the more open they are. Their density decreases. As the particle becomes larger and larger, the density decreases and the shear strength decreases. So larger particles are, I'm talking about flocculated particles, are more likely to break under changes in the level of turbulence, for example, or temperature, than small particles. So if you model the strength and the strength of the one of the things that you have to model continuously as you track these distributions in the model, each particle its shear strength is tracked. So you know at every time step what is the shear strength of a particle of any given diameter. So you do that, and then of course the shear strength decreases with size. So if the shear stress is constant, then larger particles will break first, and then the smaller particles. So it's very much a function of the shear strength of the particles.
Gerardo just add some explanation to his question. He say, my question is related to the individual particles.
Well, the individual particles, no, they are not affected, obviously, because they are solids, and their mean free path, I mean, they may be a little hotter or colder. They are not nearly as important as the flux. So I agree with you that individual particles, we are not talking about individual particles here. We are only talking about flux. So when it comes to solid particles like sand, or even micron-sized particles like less than 10 microns, like quartz or silica, glass, crushed glass or silica or whatever. The temperature effect is not something that plays a significant role, to the best of my knowledge, as it does when it comes to flux, right?
Okay, thank you, Professor. This one is from Francisco Alcocer. Professor, your modeling is only for organic sediments?
No, it's no. Actually, this is for the sediments that were collected in the estuary. They are about it's mostly mineral. It's about 5-6% organic matter, but you have to measure the properties. Like you have to measure the strength, and whatever it is that you have, you measure the properties of density, strength, whatever. But what happens is that even if you have 5-10% organic matter, that becomes really a big controlling factor, because the EPS, the long chain polymers, they kind of they bind these particles together, and all kinds of things happen. So their effect is much more than proportional to their presence in a sediment. So if you think that, if one thinks that, well, only 10% of the sediment is organic, so we won't worry about it. Well, in fact, it does have an effect. So the best thing to do is to collect the flocks and measure their properties as they are, and then put them in the model.
Okay, thanks. We have a question from Susana Binson. Could you tell us something more about your flocculation model?
Well, that's the one that I mentioned. I will send her the paper. I thought I answered that question.
Yeah, I think. This is from another question from Ramon Cantalis. Is
Yes.
there some observation about temperature in tidal flow?
Would repeat that question, please?
Is there some observations about temperature in tidal flow?
Well, well, so that's why what I was mentioning earlier is that if somebody has studied an estuary where they have taken measurements in summertime and taken measurements in winter time, and there is a 15-20 degree difference in the temperature, then that effect will for sure be present in the transport of sediment. The problem is that it is not easy to determine what effect temperature has on that particular sediment, especially if it contains biological components. So the fact that measurements are available for sediments in estuaries as a function of temperature doesn't mean that we understand how to actually correlate one with the other. And so that's where I'm saying that more field work could be specifically targeted towards understanding how to separate out the effect of temperature on different types of sediments and so on and so forth. But data are available, but I don't think that those data are necessarily one can't just take those data and start modeling with it.
Okay, thank you. This is from Francisco Pedocchi. Very interesting talk, Professor Mehta. Would you say that adding temperature would be an engineering way to introduce chemistry and biological activity into sediment transport?
Correct. Yeah. Very much so. Yeah. You have to, most civil engineers don't have any. Well, I wouldn't say don't, but they are less interested in chemistry than in mechanical systems. And I think that's a problem when it comes to cohesive sediments, because when you get down to these kinds of problems, there are many problems in hydraulics of fine sediment transport that can be solved without worrying about chemistry. But when you start talking about temperature, then I think a knowledge of uh, chemistry, especially physical chemistry related to electrochemistry, rather, is important. And I think many of you know Claire Chassain at TU Delft, and I know Federico knows her, and I think she does work in that area, and so it's important to work with people who have background in clay physical chemistry to be able to proceed with understanding the effect of temperature on sediments where the forces, surface forces are very important.
Okay, Professor, thank you. This is another question from Mohsen Soltapur.
Okay, right.
Is there any interference in the process by the salinity of water? For example, as we move in an estuary from river towards the sea, does the effect of temperature on flocculation change?
Well, there is when it comes to salinity, the problem with the salinity thing is as follows. There is flocks have. I know he knows the answer, but I'm just trying to rephrase it for everybody. That in the flocks you have pore water, and the osmosis which controls the concentration of ions, including salinity, inside the flock is a very slow process. So quite often what happens is that you have flocks and then they go up during tide and they come down during tide, and they go through different salinity fields, that is salinity of the water. So now you have a lot of times you have situations where there is disequilibrium between the pore water and the outside water. So that sets up fluxes, you see, and then fluxes of salt. It's like going through the membrane-like process between the pore water and the external water. And the flux is then the effect that has on the flux depends on the time, the residence time of those a given flock in the water, a given salinity. So that is a very difficult problem to model. I don't think from an engineering point of view, it even makes sense to worry about that. So what we normally do is, if the salinity is about 2-3%, but the flocks do, if you keep flocks in salt water for a long time, and if you measure their properties, then up to about 10 parts per thousand or so, they are affected, and above that not. So if the sediment is flocculated, in engineering calculations, we don't worry about the effect of salinity because it changes so rapidly. But the fact remains that temperature changes the ionic free path, molecular path, and so all these processes like osmosis and others, they are affected very much by temperature. So the answer is yes. I mean, the temperature does have an effect on all of these processes, but I think it's more of a scientific endeavor, but it's certainly something that needs to be looked at. Yeah.
Okay, Professor, thank you. This is another question from Kan Kuka. Very interesting thought, Professor Mehta. Will the effect of particle collisions be different in different lab setups? There are some annular flume studies reporting a decrease of settling velocities.
Well, in an annular flume, you can change the shear rate. So when the shear rate is low, flocks grow. When the shear rate reaches about 20, 30, 40 hertz or inverse second, then they start breaking up. So it all depends on at what velocity you run the annular flume. The thing about the annular flume, of course, is that its flow field is very complicated. So it's probably not the best way to study the effect of flow shear on flocks, because the flocks near the bottom have a different flow field than at the top. But if you can characterize the field, I think there is modeling has been done to characterize the flow field in the annular flume. Then you can look at at what time you withdraw sample from where and what is the shear rate at that level and so on. So if you can do such more detailed measurements, you can probably resolve those discrepancies that you are talking about between, some annular flumes settling velocities increasing and some decreasing and so on. It's a matter of characterizing the system hydrodynamics in a better way than what normally people do.
Okay, Professor, it is the last question from Alexander Segura. Professor, please can you expand the way in which the distance reached by the sediments of the Juan de Fuca in Washington River was determined when they entered the sea?
Nobody determined it, I just calculated it. I use the settling velocities to, when water comes out of a mouth of a river, it spreads like a fan. And the finest particles go as far as they can and they settle down. So I knew I made some assumptions about the settling velocity of the sediment in that river, and I assumed what would happen at ebb tide when the water is going out, how far the sediment will go in 10 degrees Celsius and 20 degrees Celsius, because in that 10 degree difference, there is a fair bit of difference in the settling velocity of the flux. So the calculations are strictly based on the knowledge of the settling velocities, but I do not actually, the system is more complicated than you can think, because the straits of Juan de Fuca, they also have currents back and forth. So I didn't include any of that. So it's really not a realistic example of that particular system. What I was just trying to show is that if you change the temperature in a system as small as that one, if you ignore everything else, I mean, you can at least show that the sediment will go further out or less out depending on the temperature. But if you want to study that one, you'd have to do a lot more measurements. And even that system, even though I call it less complicated, because there are waves outside, even though they are not always that big, can be fairly complicated. But it's much easier to model that than to model some big systems like, I mean, you have at the other end, you have La Plata River, that those kinds of things are almost impossible to model at this stage of research unless you make some big time assumptions. Yeah.
Professor, a last one this is from Yogi, so I have to do it. Ashish, do you expect the flux size change to be measurable significant in a plume such as Elwha River, suppose?
Yes. Yes, I do expect them to vary between summer and winter. Yes. Is that the question?
Yeah.
I mean, yeah. If the question is if there is a variation in the size of sediment in the river, I would say that if one were to do a comprehensive set of measurements at different times of the year and different stages of tide, I think you can actually find a detectable difference, not only because of the mineral sediment, but because the biotic component of the sediment changes between seasons.
Okay. Well, Professor Ashish Mehta, thank you very much for your great presentation. It was very illustrative. Many open questions in this amazing scientific field. Many people who want to work continuing research on the field. It was great having you here. I want to thank to everyone for attending this session of PiA webinar. Remember that we are going to present another speaker next month. We are going to send you information very soon. And thank you, everyone. And See you next month. Thank you, Professor Mehta.
Thank you. Bye-bye.
Bye-bye.
Los siguientes contenidos de Uninorteco te pueden interesar. No olvides suscribirte a nuestro canal.